Hello everyone and welcome back to the channel. So this is the third problem of the series and today we will be discussing path with minimum effort. So let's first try to understand the problem. So the problem simply states that we start a journey from the top left cell and we have to reach the bottom right cell. So it simply states that if there are m rows and n columns in the grid, then we have to start a journey from 0, 0 and reach m minus 1, n minus 1. Now while doing this, we from each cell we have four options. We can either move up, we can either move down, we can move left, or we can move right. And the effort or the cost of traveling a path is the maximum absolute difference between any two adjacent cells in the path. So for instance, let's assume that this is the path that we followed for going from the start to the end cell. So the maximum absolute difference between any two adjacent cells in this path is 5 minus 3 or 3 minus 1. So 5 minus 3 and 3 minus 1 both are equal to 2. So the maximum absolute difference between any two adjacent cells in this path is actually 2. Let's take another path. Let's assume that this is the path we followed. Now we can see that the maximum absolute difference between any two adjacent cells in this path is 5 minus 2. So 5 minus 2 gives 3. So the effort for covering this path is actually going to be 3. So let's take another path. Let's assume that this was the path that we followed. So the maximum absolute difference between any two adjacent cells in this path is actually 8 minus 2, which is 6. So the total effort for traversing this path is going to be 6. So among all these different paths having different effort associated with them, we need to find a path which has the minimum effort. So let's try to do a little dry run, or let's try to proceed and let's see if we can come up with some logic for finding the path. So we start our journey at this cell. So we are at 0, 0. So what are the options here? We can either go to this cell or we can go to this cell. So the next possible options are 1, 0 or 0, 1. So what is the cost of traveling from 0, 0 to 1, 0? Basically this. So the cost of traveling from 0, 0 to 1, 0 is actually 3 minus 1, which is 2. And the cost of traveling from 0, 1 and the cost of traveling from 0, 0 to 0, 1 is actually 2 minus 1, which is going to be 1. So now we have two possibilities to explore further. Now in this case, which cell do you think should we pick up first to explore the further path? So it actually makes sense to pick up a node or pick up a cell which has least effort associated with it. Why is that? Because we know that we were able to reach this 0, 1 in just one cost or effort equal to 1. So there is a possibility that we have a path from 0, 1 to the end cell, and in this path every adjacent cell does not have an absolute difference greater than 1. So if that is the case, in that case we'll be able to traverse from our starting cell to the end cell in just one cost. But we already know that for this cell, the cost it took to reach this cell was actually 2. So there's no way that any path going from this cell to the final cell will have a cost less than 2, because it actually took 2 costs to reach this cell. So if this cell is going to be part of any path, then the cost for that complete path has to be greater than 2 or equal to 2, because in that path there is going to be two cells whose minimum absolute difference is going to be 2, and since we have to take the maximum absolute difference in the path, the minimum value at least is going to be 2. So it makes sense to always explore the cell which has a minimum cost associated with it. So now that we have understood that from the pool of prospective nodes, we should pick up the node which has the least cost associated with it. Uh, it kind of gives us an idea that how heap can be used. So if we keep the pool of possible nodes or prospective nodes in a heap, and and this heap has to be a min heap, and we extract every time we extract the top element, the heap is going to give us the element with the minimum associated effort, and that's how heap can be used in this particular question. And actually this is quite similar to one of the graph algorithms. In graph there's a lot of times when we need to find the shortest distance or the least cost path from the starting node to the end node, and every time when we are exploring a path in a graph from the starting to the end node which has the least cost, we kind of use a similar approach where we keep a priority queue and we explore path based on the effort associated with the path. So we always first explore the path which has a smaller effort associated with it. Now let's quickly look at the code for this problem. So this is the main method, minimum effort path, which is going to be called, and this method needs to return the answer. And as input we have been provided with a 2D matrix, and this 2D matrix contains the height for each of the cell. Now as we have already discussed that we need to use a min heap in this particular problem, and the priority queue by default mimics a max heap. So as we discussed in our previous video, there are actually two ways to make min heap in C++. So the first method was a quick method or a naive jugaad you can call. So in that what we do is we actually do not push the values but we push the negative of the values, and by doing that the max heap, even though the priority queue is mimicking a max heap, it actually starts behaving like a min heap, and whenever we pop the element or whenever we get the root, we just take the negative of it to get the actual value. And I also mentioned that there's another more proper way where we can use the proper C++ syntax to actually initialize a min heap. So this is the syntax for initializing a min heap. Now this min heap is actually going to store a pair of int comma pair, and that pair also stores int comma int. So basically each node in my heap is going to look something like this. And why I have used this data structure as the data structure for the node, because the first value actually represents the effort, and these two values actually represents the coordinates for each cell in the matrix. So every time that we push a value to a heap, it is going to contain the effort required to reach to that point and the coordinates of that point. So what extra syntax that we need to keep in mind while declaring a min heap? We need to pass these two parameters, vector and greater, and these should have the same data type, which is the data type for our heap node, which is pair int comma pair of int comma int. So we have to pass these two parameters as well during initialization to actually define a min heap. Now the other data type that we have defined is actually a helper matrix, and this matrix is called visited, and the size of this matrix is equal to the size of our input parameter heights. So each cell in this matrix actually stores that what was the minimum effort till now to reach this cell. So if we haven't reached the cell yet through any of the paths that we have explored, then the value in the matrix for that cell will be equal to int max, or a junk value that indicates that we have not yet visited this cell, but otherwise it will store the min effort till now that was required to reach to this cell using any path. So why do we actually need a helper matrix called visited? So it is needed because if we reach a cell more than once, if we have already visited a cell and we again come to that cell, we need to know that whether it is worth exploring this cell again or not, whether do we need to put it in our heap or not for further exploration. So why will we come back to same cell? So there are two cases in which we might come back to the same cell. So first we might have visited this cell as part of a different path, and now when we are exploring a different path, we again might come to this cell through a different path. And the second case is that since our question specifies that we can move up, down, left and right in a grid, so since we can move in all the four directions, there is a possibility that if we have already visited a cell, by taking a complete circle in the matrix we might visit that cell again. So in that case we need to know whether we need to explore the path from here again or not, since this cell has already been visited. So if we think about it, it makes sense to explore a node again if the effort required to reach this cell again was actually less than the effort required to reach this cell earlier. So when is this possible? So as I said that in the first condition, when we might reach this cell as part of a different path, it might be the case that in this path the effort required to reach this cell was actually less than the effort required to reach this cell in some previous path. And it actually makes sense that we explore this cell again, because there is a possibility that we might reach the end in much less effort, because the effort till now, or the effort to reach this cell, has been reduced. But if we reach this cell again and the effort required to reach this cell again is actually same or larger than the effort required earlier, then it does not make sense to explore that path again, because the total effort for this path is actually going to be greater or equal to this effort. So it does not make sense to explore the cell again. Now in the min heap, now in the question it says that we start from 0 comma 0, and since we are already standing at this cell, the effort required to reach that cell is 0. So we initialize, or we put 0 comma 0 in our min heap, because we are standing at the first node, and we'll start exploring from 0 comma 0. And we also mark visited of 0 0 as 0, because we have already visited this cell 0 comma 0, and the effort required to reach this cell was 0. So we have initialized both, we have initialized that value in the matrix, and we have added the node to our heap. Now this is a helper vector. This is just a technique to make it easier to explore all the four neighbors, because we can move up, down, left and right, and the each vector inside this vector dirs is actually representing a way to move to one of the four neighbors. So 1 comma 0 is basically so if we are standing at x comma y, then 1 comma 0 is actually representing x plus 1 comma y, which is going to be a cell downwards, and 0 comma 1 is again representing cell x comma y plus 1, so which is representing a cell on the right. So this helper vector is nothing but a easier way to explore all the four neighbors, and you'll see how it is easier. So this is the main loop, and we have already discussed that we'll be exploring nodes in the order of the effort required to reach the node. So we'll first explore the node which required minimum effort to reach. So that's why we take the top element from the min heap, or the root element for the min heap, which is basically the node with the least effort. So we just take the effort to reach that node and the xy coordinate for that node, and we also pop that node from the heap because it is no more required, we are exploring it now. So we just remove the root from the heap. Now we first need to check if this current node is actually the last node. If this current node is actually the last node, then we just return the effort. Since we are exploring the nodes in the order of effort, like in ascending order of effort, so we are exploring nodes with the least effort first. So any node that is going to come after this, or any path that is going to come after this, will actually going to have a higher effort. So since we have already reached the last node, it does not make sense to explore any further, because those paths are going to have an effort equal to this effort or larger than this effort. So we directly return the effort if we have reached the last node. If we have not reached the last node, then we will check all the four neighbors. So this is how we are using our helper vector. So every time we take one of the vectors from this helper vector dirs and we add it to our coordinate. So every time we add it to our coordinate, it gives one of the four neighbors. So the first vector inside dir is gives the neighbor which is below this cell. The second gives the neighbor on the right side. The third vector actually gives a neighbor which is above this node, and the fourth gives a vector which is on the left side of this node. So every time we pick one of the four neighbors, we first check that whether the coordinates for this neighbor are within the bounds of the matrix. If this neighbor is outside the bound of the matrix, then it is not a prospective node to explore further, so we do not add it to our heap. If it is inside the bounds, then what we do is that we calculate the effort to reach this node. So the effort needed to reach this node is actually the maximum of the effort required to move from the previous node to this node, and the effort required to reach the previous node. So whichever of these values is maximum is actually going to be the effort to reach this node. And as we have already discussed, it makes sense to explore this node further if we have not explored this node before, or we reached this node before but the effort required to reach this node before was actually greater. So if we if we are visiting this node first time, or the effort required to reach this node is actually smaller than the effort required earlier, then we need to again explore this node, and we again add it to the min heap. In case if none of these conditions are satisfied, then we do not add it to the min heap, because it's not a prospective node and it would not make sense to explore this node again. And if once we are done with this whole computation, and while traveling and while exploring all the nodes we were never able to reach the last cell, then we'll never return anything from this loop, and this loop will end and we'll land on this step. So we have just returned -1. But actually this is not going to be a case, since there are no blockers in the matrix. We'll definitely reach the end cell. The effort might be high, the effort might be less, but one thing we can be but there's one thing we can be sure of, is that we'll reach the last node somehow. So ideally, or by logic, this statement will never get executed. We'll always return some effort from here. But yeah, we have just kept it as a safety, that in case we were never able to reach the last cell, then we'll return -1. So let's discuss the time complexity for this. So as we know that the total amount of elements that are going to be there in the heap at any time is, in the worst case, is going to be equal to the total number of cells in the matrix. So the total number of cells in the matrix is m into n. So the total number of elements in worst case in the heap are going to be m into n. So if the total number of elements in heap at any time are going to be m into n, this loop maximum is going to run m into n times, and in every loop we are actually popping the elements, or doing calling the extract or delete method on the heap, which takes log of m into n times. So since this loop in the worst case is going to run m into n times, and within each loop we are extracting from the heap, which in worst case is going to be of size m into n, so the total time complexity turns out to be big O of m into n log m into n. So this is the time complexity for this solution. So I hope that you guys are finding these videos helpful and you're actually learning something while watching these videos. And I'll soon be back with the last video for this series, and in that video again we'll discuss another problem for heap, but this time a harder problem. So see you in the next video guys. Till then, take care, keep learning, bye bye.